January 1942. Somewhere in the black water between Halifax and Liverpool, beneath a sky that no longer promised dawn. The convoy moved in silence. 43 merchant ships arranged in columns like a herd sensing wolves. Their cargo, grain, steel, fuel, timber, the metabolic substance of Britain's survival. Above them, nothing. Around them, nothing. And below, always below, the invisible equation of death. Every 12 hours, another ship disappeared. A flash, a scream of tearing metal, then the cold swallowing of men and tonnage into the Atlantic's indifferent algebra. The crews no longer spoke of odds. They simply sailed and waited and died in patterns they could not see. 3,000 miles west, in a limestone building on the edge of Washington, a man sat surrounded by failure. His name was not yet known to history. His desk bore no medals, no commissions, no evidence of rank. Only paper, reams of it, covered in symbols that resembled music notation more than war. He had been told twice now that his work was theoretical nonsense, that mathematics could not hunt submarines, that numbers, however elegant, could not explode. His colleagues in the Anti-Submarine Warfare Operations Research Group had begun to avoid him at lunch. Some thought him brilliant but impractical. Others thought him mad. His supervisor had recommended reassignment. The recommendation sat in a folder, awaiting signature, on a desk 3 floors above. The man's name was Philip Morse, and he was counting corpses in reverse. By the winter of 1942, the Battle of the Atlantic had become a mathematical genocide. The numbers told a story more terrible than any John bot. In 1940, German U-boats sank 471 Allied ships. In 1941, they sank 875. By March of 1942, tonnage losses exceeded 500,000 tons per month, faster than American and British shipyards could replace them. Admiral Karl Donitz, architect of the U-boat campaign, had calculated the equation himself. Sink 700,000 tons monthly, and Britain would starve into surrender within a year. He was ahead of schedule. Churchill would later write that the only thing that truly frightened him during the entire war was the U-boat peril. Not the Blitz, not Dunkirk, not the fall of France. This silent mathematics of drowning. The Allied response had been instinctive, traditional, and catastrophic. Convoys sailed in tight formations, believing safety in numbers. Destroyers patrolled in set patterns, sweeping back and forth like mechanical sentries. When a submarine was detected, warships dropped depth charges in clusters, 5, 10, 15 explosives, detonated at estimated depths, saturating an area in the hope that probability would do what precision could not. Doctrine stated, where there is sea, put explosives. It was hunting by volume, by drowning the ocean itself. And it was failing. The U-boats were winning not through superior technology, but through superior invisibility. They operated in the gaps, between patrols, between detonations, between doctrine and reality. They slipped through search patterns like water through a gnat. For every U-boat sunk, 5 merchant ships died. The mathematics favored the hunter. And mathematics, in war as in nature, is crueler than courage. Philip Morse understood this. He understood it the way a composer understands that music is not notes, but the space between them. He had come to the Navy from MIT, where he had taught physics and studied wave propagation, how energy moves through mediums, how vibrations reveal structure. Now he stared at convoy loss reports as if they were seismographs. Patterns emerged, not tactical patterns, but statistical ones. Ships died in clusters. Sinkings occurred at specific intervals. U-boats appeared and vanished according to rhythms that suggested not randomness, but geometry. He proposed something radical, that the war at sea could be modeled, that submarine hunts were not chaotic encounters, but probability distributions. that depth charges were being deployed according to assumptions about U-boat depth, speed, evasion tactics that had never been tested. He asked for data. He received skepticism. He asked for access to patrol reports. He received fragments. He asked for permission to analyze attack effectiveness. He received a polite suggestion to focus on something more practical, like radar calibration. But Morse did not stop. He could not, because he had begun to see the shape of the thing. And the shape was killing thousands. Spring 1942. A U-boat commander's diary, recovered years later from the wreckage of U-507, described the hunt with unsettling confidence. The convoys are blind. They zigzag according to schedule. Their escorts sweep in arcs we have charted. When the destroyers approach, we dive to 90 meters and wait. They drop their charges at 50. We hear them, distant thunder, like a storm passing overhead. Then silence. Then we surface and resume the hunt. It is almost routine now. The mathematics favor us. For every hour they search, we have 20 hours of darkness. Routine. That word appeared again and again in recovered German logs. What the Allies experienced as terror, the U-boat crews experienced as procedure. They had learned the Allied patterns. They knew that depth charges were set shallow, optimized for submarines caught on the surface or in hurried dives. They knew that search patterns were linear, predictable, easy to evade. They knew that probability, left unexamined, favors the hidden. Morse began with a simple question. At what depth do U-boats actually operate when under attack? No one knew. Doctrine assumed 50 meters, because early submarines were fragile and slow to dive. But U-boats in 1942 were Type 7 and Type 9 models, capable of reaching 200 meters, fast diving, and equipped with silent running systems. The doctrine was obsolete, yet the depth charges remained set to doctrine. Morse requested data from every depth charge attack in the Atlantic for which records existed. He was granted access to a fraction. From that fraction, he began reconstruction. He analyzed attack geometries, time to detonation logs, and, critically, the rare reports where U-boats had been damaged or sunk. He mapped the depth at which successful attacks occurred. The distribution was stark. Almost no kills happened at 50 meters. The majority clustered between 90 and 120 meters. The U-boats had adapted. The doctrine had not. He wrote a report. It was 11 pages, dense with equations and probability curves. Its conclusion was a single sentence. Depth charges should be set to 100 meters as default, with pattern spacing optimized for deep-water probability fields. The report was filed, then ignored, then briefly ridiculed. A senior destroyer captain wrote a rebuttal arguing that deeper settings would waste explosive force, that shallower detonations created better surface effects, and that mathematical theory has no place in the practical art of submarine warfare. The rebuttal was circulated. Morse's report was not. But war has a way of auditing its own failures. In April 1942, a single wolf pack sank 22 ships in 72 hours. The numbers reached Roosevelt. He demanded answers. Someone, somewhere in the labyrinth of Navy bureaucracy, remembered the physicist's report. It was retrieved, reconsidered, and, finally, tested. May 1942. HMS Hesperus, a destroyer operating west of Iceland, received new orders. Set depth charges to 100 meters. Recalibrate spacing to Morse's specifications, a pattern that prioritized depth over surface area, precision over saturation. The crew thought it suicidal. Deeper charges meant less visible water disturbance, less immediate feedback, less psychological reassurance. It felt wrong, but the order was explicit. On May 11th, sonar detected a submerged contact. Hesperus maneuvered into attack posture and dropped a pattern. The detonations were muffled, distant, almost disappointing. No towering columns of water, no dramatic surface eruption, just deep, percussive thuds. Then oil, a wide-spreading slick, debris, wreckage, bodies. U-223, confirmed kill. The pattern repeated. May 19th, U-573. May 24th, U-568. By June, destroyers using Morse's depth settings had achieved a kill rate triple the previous average. The U-boat commanders, accustomed to safety at depth, began to report something new in their logs: fear. One entry, recovered from U-618, recorded the change with chilling clarity. The explosions now come from below. We no longer know where to hide. But Morse was not finished. Depth was only the first variable. He turned next to spacing, the geometry of depth charge patterns. Standard doctrine called for tight clusters, saturation bombing of a small area. Morse's probability models suggested the opposite: wider spacing optimized to the U-boat's possible evasion radius within the time between detection and detonation. He calculated the mathematical envelope within which a submarine could maneuver, accounting for speed, dive angle, and human reaction time. Then he optimized charge placement not for maximum coverage, but for maximum likelihood. It was counterintuitive. It felt like using fewer explosives. In practice, it meant every charge had a higher probability of being lethal. Efficiency over force, precision over panic. The Navy tested it. Kill rates climbed again. Then Morse addressed the final, most controversial variable: patrol patterns. Destroyers escorted convoys by sailing back and forth in predictable arcs, a visible, reassuring presence. But visibility was not the same as effectiveness. Morse's models showed that randomized, unpredictable patrol routes generated far higher detection rates because they denied the U-boats the ability to chart safe windows. A submarine commander could time a regular sweep. He could not time chaos. Convoy commanders resisted. Randomness felt like abdication of control. It looked disorganized. It undermined the appearance of vigilance. But appearances, Morse argued, were not sinking U-boats. Probability was. In July 1942, the first convoys adopted randomized escort patterns combined with deep-setting depth charges and optimized spacing. The results were immediate. U-boat attack success rates dropped by 40%. Convoy losses fell, and for the first time since 1940, the mathematics began to shift. Donitz's equation, 700,000 tons per month, became unattainable. By August, it was unsustainable. By September, the U-boat fleet began taking losses faster than German shipyards could replace them. The transformation was not loud. There was no single dramatic battle, no midway moment, no iconic photograph. Just numbers, bending slowly toward survival. Just convoys arriving intact. Just depth charges finding their targets in the cold, dark water where, for 2 years, submarines had hunted freely. The wolf packs began to withdraw from the mid-Atlantic. Donitz rotated crews more frequently. They were returning traumatized, confused, no longer confident in their invisibility. German naval intelligence could not explain it. Their technology had not changed. Their tactics had not failed. Something else had shifted, something invisible. What had shifted was knowledge. Morse had weaponized probability. He had taken the central advantage of submarine warfare, invisibility, unpredictability, the vast empty ocean as camouflage, and turned it into a grid of likelihood. He had made the invisible calculable, and in war, what can be calculated can be killed. By the end of 1942, 30 German U-boats had been sunk using methods derived directly or indirectly from Morse's models. By 1943, the number exceeded 100. The Battle of the Atlantic, which had seemed unwinnable, tilted. Not because of a superweapon, but because of a formula. Not because of heroism, though there was heroism, but because someone had asked, what if we are hunting incorrectly? What if doctrine is simply wrong? The Allied naval establishment began to listen. Morse's operations research group expanded. Other mathematicians joined: statisticians, physicists, economists, men who understood systems and variance and error correction. They analyzed everything: torpedo reliability, convoy routing, aircraft patrol efficiency, even the optimal color to paint anti-submarine aircraft to delay visual detection. Each analysis saved lives. Each equation was a silent argument against death. But the resistance never fully disappeared. There remained, always, a tension between those who trusted experience and those who trusted evidence. Convoy captains who had survived by instinct resented being told that instinct was statistically suboptimal. Decorated officers found it intolerable that a man who had never been depth-charged could dictate attack doctrine. The resentment simmered. Morse received letters accusing him of cowardice, of dishonoring the sailors who died before his formulas existed, of reducing warfare to cold abstraction. He kept them, all of them, in a folder he never showed anyone, because he knew something his critics did not: that mathematics is not cold. It is the opposite. It is the refusal to accept unnecessary death. Every variable he optimized, every probability curve he calculated, was an argument that the lives lost before were not inevitable, that they could have been saved, that doctrine had killed them as surely as torpedoes, and that knowledge, however painful, was the only honest form of remembrance. There is a photograph, rarely published, from the autumn of 1943. It shows the deck of a destroyer, name redacted, somewhere in the North Atlantic. The crew is gathered around a depth charge rack. The charges are being set. The sailor adjusting the depth mechanism is young, perhaps 20, his face wind-burned and exhausted. On the casing of the charge, someone has chalked a number: 100 meters. Just that, a number, not a name. Not a slogan, just the depth. The depth that mathematics had determined was correct, the depth that had, by then, become routine. In the photograph, no one is smiling. There is no triumphalism. They are simply working, setting the charges, preparing the pattern, doing what the equations said to do. And somewhere below them, invisible, a submarine was making calculations of its own: how deep to dive, how long to wait, how much ocean lay between survival and detonation. Two sets of mathematics, opposed, but only one had been tested against evidence. The sailor in the photograph survived the war. In an interview decades later, he was asked if he remembered when the depth settings changed. He did. He remembered the skepticism. He remembered the first kill using the new settings, the oil slick spreading like proof. He remembered thinking, someone, somewhere, did the math, and the math was right. He did not know the name Philip Morse. Few did. Operations research was classified. The formulas were not published. The men who created them received no medals, no public commendations, no place in the popular memory of the war. When the war ended, Morse returned to MIT. He taught. He published papers on acoustics and quantum mechanics. He never spoke publicly about the U-boats. When students asked about his war work, he deflected. "I did some consulting," he would say. "Statistical analysis." Statistical analysis. As if that phrase could contain what it meant: that he had taken the chaos of the Atlantic, the terror of the convoy sailors, the impossible vastness of submarine warfare, and found within it a structure, a pattern, a solution. That he had done what the entire naval tradition of centuries had not. He had made the ocean legible. By the spring of 1944, the U-boat threat had been effectively neutralized. Convoys crossed with increasing impunity. The loss rates that had once threatened Britain's survival had fallen to sustainable levels. Donuts, facing catastrophic submarine losses, withdrew the wolf packs from the Atlantic and redeployed them to coastal defense, a strategic admission of defeat. The battle was over. Not because the Allies built more ships, though they did, not because of superior technology, though that helped, but because the mathematics of the hunt had been rewritten. And yet, in the official histories, Morse's name appears rarely, if at all. The victory in the Atlantic is attributed to radar, to aircraft, to the courage of convoy escorts. All true, but incomplete. Because beneath those tools and that courage was a framework, a way of thinking about uncertainty, about probability, about the difference between what feels right and what is right. Morse had built that framework, and it had killed submarines. There is a deeper truth here, one that extends beyond depth charges and U-boats. Morse's work represented a fundamental shift in how war could be understood. For centuries, military strategy had been the domain of experience, instinct, tradition, the accumulated wisdom of warriors. Operations research proposed something radical, that war could be studied like physics, that human conflict, however chaotic, obeyed patterns, that those patterns could be modeled, tested, optimized, that the scientific method, applied to killing, could save more lives than it cost. This was not a comfortable idea. It suggested that generals could be wrong, that doctrine could be obsolete, that the instincts honed over decades of service could be less reliable than a formula produced by a man who had never fired a shot. It implied that war was not an art but a system, and systems could be analyzed. The tension between these worldviews never fully resolved. Even today, military institutions struggle with the balance between human judgment and algorithmic precision. But Morse's work proved that both were necessary, that courage without knowledge is waste, that experience without evidence is superstition, that the deaths of sailors, however brave, mean nothing if the tactics that killed them are never questioned. There is a final detail, small and easily overlooked. In 1943, the Navy published a manual on anti-submarine warfare incorporating Morse's methods. It was distributed to every destroyer and escort vessel in the Atlantic Fleet. The manual was dense, technical, filled with charts and probability tables. But on the first page, in the introduction, there was a single paragraph, unsigned, added by someone unknown, that read, "These procedures were developed through the analysis of operational data and the application of mathematical methods. They represent not theory, but tested knowledge. Every value, every setting, every recommended pattern has been derived from evidence. The men who developed these methods did not serve at sea, but they served those who do. This manual is their contribution to your survival." The paragraph was removed in later editions. Someone decided it was too sentimental, too sentimental. The formulas remained, the context did not. And so, Morse's work became invisible in the way that foundations are invisible, essential but unseen. The destroyers that used his depth settings never knew his name. The convoys that arrived safely because of his patrol patterns never knew why they were different. The sailors who survived did not know that survival had been calculated. But somewhere in the black water of the Atlantic, in the space between what was and what might have been, 30 German submarines lay silent on the ocean floor. 30 machines of war, stopped not by superior force, but by superior understanding. 30 proofs that mathematics, however abstract, could be a weapon, and that knowledge, however quiet, could turn the tide. Philip Morse died in 1985, at the age of 83. His obituary in the New York Times mentioned his work in acoustics, his tenure at MIT, his contributions to quantum theory. The U-boats were not mentioned. The depth charges were not mentioned. The thousands of lives saved by his formulas were not mentioned. He had requested it that way. He had always believed that the work mattered more than the name, that solutions were more important than credit, that the silent application of reason to the problem of death was, in itself, a kind of dignity. But history remembers in strange ways. In the archives of the Naval War College, there is a folder labeled ASW Operations Research, 1942 to 1943. Inside are reports, data tables, graphs. And clipped to one of them, in handwriting that has never been identified, is a note. It says, "This man saved more sailors than any admiral, and no one will ever know his name." That is not entirely true. Some know. Those who study the war beneath the war of logistics and probability, of silent variables and invisible optimizations, they know. They know that the Battle of the Atlantic was won not only on the surface, but in the calculations beneath. That every convoy that arrived, every U-boat that failed to return, was a data point in an equation that someone, somewhere, had solved. And in that knowledge, there is a truth larger than tactics. That freedom is not only defended by those who fight, but by those who think. That democracy survives not only through courage, but through reason. That the refusal to accept unnecessary death, the insistence that loss can be studied, understood, reduced, is itself a form of resistance against the darkness. The U-boats hunted in silence, but they were defeated by something quieter still. A man at a desk, counting corpses in reverse, refusing to believe that mathematics could not save lives. And in the end, it did. Not dramatically, not visibly, but completely. Somewhere in the Atlantic, the water is very deep and very cold and full of things that sank long ago, machines and men and certainties. And among them, invisible as always, are the equations that made the difference. Still there, still true, still waiting for anyone willing to listen.